Yes, thank you very much. Also, thanks to the organizers for having me here. Indeed, so that's the second experimental talk of this afternoon. And I will be talking about a different platform, but there will be also a few of these ideas of actually combining digital and analog, at least showing to you the tools. So I fully agree with the statement that you have heard earlier. I think this is really starting to blend over, like we don't make such a big distinction anymore necessarily. Okay, so the big difference that we have here in this experiment is that it is a two-dimensional array of cesium atoms, and in this case, they are tunnel coupled. So we implement Hubbard-type Hamiltonians where the atoms can move around. So it's an itinerant system, and then the natural interaction between the particles is on site. And then before we take the snapshot, we freeze the atoms in plane. So this is a schematic of the two-dimensional lattice. We freeze all the hopping dynamics, and then we shine in near resonant photons in order to collect fluorescence photons on a camera. And then we get images like this, where you see the individual cesium atoms in the lattice. I just want to highlight briefly that this is a very different regime in a sense that what we are trying to resolve here, the distance between neighboring atoms is 380 nanometer. So it's really, really tiny because we really want to have large tunnel coupling between neighboring sites. Now, we have in our experiment two objectives for two different purposes, one for imaging, but we can also use the objective from below in order to project high-resolution programmable potentials into the atomic plane. And specifically, in our case, we use cesium atoms. So this may be a technical detail, but it allows us to tune this Hubbard on-site interaction energy U. And we make use of bichromatic superlattices. So along each axis, I've shown you this square optical lattice. We overlap another one so that we can implement dimerized hoppings along X and Y, and can also implement on-site potentials on every other site. So essentially, our lattice has a four-side unit cell in the end that we can control in terms of the couplings and the on-site potentials. And this potential from below that we project into the atomic plane, we make a repulsive box in order to really realize homogeneous square lattices where the bottom of the trap is flat. So what we want is a homogeneous lattice that doesn't have like any harmonic confinement. And so the atoms are confined in plane by just projecting sharp balls into the atomic plane. So what you see here is a Mott insulator of n=1 atoms per site at 98% filling. So we have a few holes in the system. And so this is an actual image of about 2,500 atoms, how it looks like in the experiment. The previous image, you saw individual atoms because we increased the lattice constant by 2. If we work in the closely spaced lattice, it's a bit more challenging to resolve, and we use machine learning to do this reconstruction. So if you're interested, you can look at this paper. I think it's yet another direction that is particularly interesting to look into because it's a sub-wavelength array, meaning that we get a lot of collective light scattering effects. The wavelength of the light-induced dipoles is 852, and the spacing is only 380. So we are very deep in the sub-wavelength regime where you could study superradiance, subradiance, and all these kinds of phenomena. I will not really talk about this today, but it's interesting that our machine learning network actually learned all these collective light scattering phenomena. This was something for us to work on. Okay, so this is our experimental platform. So essentially what we can do is realize these large two-dimensional arrays. We can apply programmable potentials, fairly side-resolved, so it depends on the operation that we want to do. And we can apply operations using the superlattice potential or isolate like ladder systems to study dynamics. And this is also something that we have done in the last two projects, which I just briefly want to flash here because I don't have enough time to explain all of them. Here we studied quench dynamics in an isolated ladder system. So here we take our two-dimensional array and only couple every other pair of chains to each other. And here we looked at the emergence of fluctuations of particle number fluctuations in subsystems in order to extract diffusion constants in this coupled ladder systems. A second project that we have worked on recently is combine these ladders with artificial magnetic field. And we have realized strongly correlated Meissner phases in these systems that are characterized by emergent chiral currents at the boundary of the system, which we have measured with a technique that I will explain in the following. So here I will mostly talk about non-equilibrium physics and novel observables that allow us to extract information in the second case, in a thermodynamic limit, about the properties of the quantum many-body system that we have prepared in the lab. So I will mostly talk about these two projects and start with the first one, which was motivated actually by all these topological physics, where a lot of properties show up in non-trivial current patterns and not in the density. So in particular, the strongly correlated Meissner phase that I've briefly mentioned to you, it has a flat density profile, and the information is encoded in these chiral currents that we would like to see. And typically, if we take our microscope images, what we have access to is occupations. So the question is, how can we go beyond that and measure something that is sensitive to the phase of the wave function between neighboring sites? And in order to get access to this, we do not stop our experimental simulation here. So we run the quantum simulation experiment, but then we insert another step. We project this two-dimensional lattice and form a two-dimensional array of coupled dimers. So what we do is we suddenly switch off all the tunnel couplings along Y and every other tunnel coupling along the X direction, such that there's still dynamics going on, but only between two neighboring sites. So this allows us to implement a rotation in order to change the measurement basis before readout. So this is exactly what we do. And I can briefly explain this in a two-level scheme on a Bloch sphere. Since the dynamics only happens between two neighboring sites, we can label them as left and right and put them on a Bloch sphere. And the dynamics within each one of these double wells, we can fully control by changing the parameters of the lattice. Now, if you just have one isolated dimer and it's symmetrically coupled, in the spin language, this would be a sigma x rotation. And if you apply a potential energy difference between these two sites, in the spin language, it would be a sigma z operation. Now, the shape of this potential we can control by changing the relative phase between the two standing waves that we project onto our atoms. So we can dynamically control these parameters and also decide for how long we turn these couplings on. So in the end, we have this double well Hamiltonian, which allows us to then perform arbitrary rotations on this Bloch sphere, where we put the left side of the double well on the right side of the double well on the poles of this Bloch sphere. Now, in a typical measurement, where we just extract occupations, we would measure the expectation value of sigma z. So in this simple double well picture, it would be the imbalance between neighboring sites. And if we look at this sigma x operator, well, I told you it's just a symmetric coupling between the two sites. So that actually gives us access to the kinetic energy. So if we re-express this operator in terms of the Hubbard operators, A dagger A, which encode the tunneling between neighboring sites, we can get access to this quantity as well. Or if we look at sigma y, this gives us access to the current. So what we can do is, after we have prepared our many-body wave function, is we can project it onto this dimer lattice, and then, for instance, apply a pi/2 rotation around the x-axis. And that means the current, or the information that is encoded in the current, will be rotated onto the z-axis, which is our measurement basis. So then we can just do our usual projection measurement and see the current amplitude in the occupation. Okay, so this is actually a single site resolved measurement. So we can do this on all the bonds in parallel. And we have our microscope objective, so we can generate a local map of currents and also extract current-current correlations or fluctuations of this quantity. And this is what we did for the topology experiment, but we could really perform arbitrary rotations there.
Single site, which
but
okay, so it won't fluctuate much in that case. Because
well, in this case, it's like binary,
exactly,
right?
Yeah.
Exactly. And so in order to just demonstrate how well this works, you can play with different types of sequences that you are very familiar with in a different context, but now with itinerant particles on a lattice. So for instance, we can look at spin echo type sequences where we put a particle initially on the left-hand side, then we apply a pi/2 rotation, we let it precess in the equatorial plane, as we would do in a normal Ramsey type experiment. Then we can apply a pi pulse by rotating around the x-axis, let it process during the second half of this sequence, and read out the state after applying another pi/2 pulse along x. So this is the standard Ramsey sequence or Ramsey protocol with a spin echo pulse in the middle, which allows us to extract the coherence time of our system, for instance. And so we know that actually in this case, I should say that this procession time is kilohertz. So it's up to like 100 interaction timescales in the system, is mostly limited by like a very slow drift of an underlying disorder potential that is present in this particular system. We had some fringes that we got rid of in the meantime. And so this is actually very nice because we can efficiently implement this in parallel over a large system, because these interfering lattice potentials, they are very clean and nicely controllable. But on top of that, we can now use the potentials that we can project into the plane in order to selectively rotate the bases in some of the double ways. So we don't have to do everything in parallel. For instance, here you see that the DMD potential that we use to project potentials into the atomic plane generates like a small potential bump, which introduces a sigma z operation into this specific double way. So then we can keep sigma x operation, for instance, in one, sigma z on the other one, and have different combinations of these rotations across the 2D plane. So we can combine these efficient global operations with a few local ones. And we did some proof of principle experiment where we engineered like a pi phase shift on every other row just to demonstrate that we can actually nicely do that, even in this crazy spaced lattice, which only has 380 nanometers between neighboring sites. Now, some of you may know that these ideas of using optical lattices and on-site interactions for computing, there are ideas for fermionic quantum computing experiments. They typically work at much larger lattice constants. And this really, for us, worked out of the box. So I'm very, very confident that for these experiments, this will just work. I think there's just no question. And it's stable. We have a very complicated machine, and still, this was like something that we got to work within, or my students got to work within a week. So I'm really confident that that's a very robust way of implementing these operations. And we have used them for readout. Just to highlight, locally rotating them, of course, then gives you access to not only like density-density correlators or current-current correlators, but also density-current correlators or any other type of observable that you would like to measure in your system. And then, of course, you can also turn this around. Like there's no reason to just apply this for readout. You could also use this for initial state preparation. Like typically the way our non-equilibrium experiments work is that we prepare an initial state, which typically is a product state, where we place particles somewhere in the lattice. And then we turn on time evolution, and then we ask questions about these quench dynamics, about the thermalization of the system, for instance. Now here, you could now use these local rotations in order to imprint coherences in your initial state or imprint currents in your initial state. And the way I've explained this technique to you, it only works on nearest neighbors, but we can shift them. So you can build more complicated sequences by first letting these pairs talk to each other, then shift it and let the neighboring pairs talk to each other, and then also do it in the perpendicular direction. So it's not confined to 1D operations. Since we have this superlattice potential in both directions, you can also cook up more complicated sequences in order to produce more complicated initial states. And so this is a very nice way to combine these ideas of like having a few digital operations and analog Hamiltonian evolution, even for these itinerant systems where we have atoms in optical lattices, which opens quite a few new interesting directions. Okay, so this is about the techniques of our platform and the observables that we can measure. Now, the application that we used was topology in order to measure these Meissner currents in many-body systems. But I will now switch gears and only talk about density snapshots. So for the rest of the talk, where we study quench dynamics, we will actually only sample from our occupation basis snapshots. And this is a collaboration where we have worked on with the groups of Markus Heil and Anatoly Poltkovnikov. where we have tried to address the question, what can we address in terms of quantities in the thermodynamic limit, or something that we can measure that teaches us something about the properties of the system in the thermodynamic limit. And Low-Schmidt-Echo is a quantity that appears in many different areas of physics. So it's something that keeps, also in experimental protocols, keeps popping up everywhere. And we try to find protocols in order to extract this information. It has a lot of applications in statistical physics, quantum many-body systems, but also lattice gauge theories. The problem is that what we need to extract is the overlap with the initial state for a system of size n. So what we would like to do is prepare the state psi0, measure this overlap after time evolution. Now, if we have a large system of, in our case, it's typically 50 sites, the problem is that this overlap decreases exponentially in system size. So it's a quantity that is extremely hard to measure experimentally and is very resource inefficient to extract. Now, what you can try to do is extract information from a smaller subsystem. So we have these long chains. And now the question is, if you look at a smaller subset, can you still learn something about your many-body system? And so these are the types of snapshots that we get. So these are raw data images. So if we start preparing a state psi0 and then turn on the time evolution, we would freeze, we take a snapshot, this projects us onto the occupation basis, and then we sample from that. So at each individual time step t, we get these different realizations, and then we can extract information from these, like mean quantities, fluctuations. And in our case, we look for fingerprints of the initial state. So what we look at is return probabilities. So we have our time-evolved state. We know our initial state, which in this case is a product state of particles that we place in the lattice. In this case, it's a translationally invariant initial state where there's a particle on every other side. We let it evolve as a function of time. And then we compute this spatially averaged projector. So Pi projects onto the on site I onto the initial state. So we look for these overlaps that we know we had in the initial state, and then we do the spatial average and extract the subsystem return probability, or Low-Schmidt-Echo. Now, this quantity is not much better in terms of scaling. So it will also scale down exponentially in system size. Yeah. In this case, yeah. And so the hope is that, you can still win if the subsystem quantity tells you or teaches you something about your many-body system. It's still tiny, but if you can learn something with its scaling, then you can still extract some useful quantities. And indeed, many of the properties or features that were revealed by looking at the full system Low-Schmidt-Echo, we find in this subsystem return probability as well. And we have looked at two different regimes, short-time dynamics and long-time dynamics, which address two very different aspects of quench dynamics. The first one, to use this quantity to reveal dynamical quantum phase transitions and try to learn a little bit more about what causes them. And the second one, to have a measure of the dimension of the accessible Hilbert space to your initial state. So the question is, this is related to the thermalization of isolated quantum many-body system. Does your initial state explore the full system? Is it ergodic? Or is it able to probe fragmentation of the Hilbert space in the presence of kinetic constraints? And again, I just want to stress this, that what we are trying to do is look at the scaling with n, which in our case is always the subsystem size, and learn something about the thermodynamic limit. Okay, so dynamical quantum phase transitions are somehow an analog of equilibrium phase transitions. So again, we look at this quantity that I've already introduced before, which is the return probability, which in our case is the subsystem return probability. And typically, if we plot this for a generic system, it just goes down as a function of time and will approach zero. Now, there are some quenches that you can implement where there's a cusp-like feature that emerges. And this is somewhat analogous to cusp-like features in the free energy for equilibrium phase transitions. Now, there's no general universal understanding of these dynamical quantum phase transitions. They often occur by quenching across an equilibrium critical point. But there are also other DQPTs that have been found. And I think there's no universal concept yet that unifies all of them. And we got excited about this because we looked at this quantity in our experiment. We found a dynamical quantum phase transition, and we used the subsystem Low-Schmidt-Echo in order to reveal the role of many-body correlations in that particular experimental realization. And so far, mostly experiments did not really look at higher order correlations at these critical points at DQPTs. Now, the system that we are working with are 1D Bose-Hubbard chains in the hardcore limit. So we start from an initial state that has this charge density wave. It's a product state 101010. The system size is 40 and U is about 25J. So it's very hardcore. This chain can be mapped onto free fermions, which allowed us to actually do all of these analytical expansions that did play a role. And so here you see the subsystem Low-Schmidt-Echo that we extract in this chain of length 40. We start with subsystem 1 and then go all the way up to 7. And then you see that indeed there's this cusp-like feature that appears. And it seems that, it becomes sharper and sharper as you go to larger and larger subsystems. Now, using this analogy of equilibrium phase transition, where we have the cusp in the free energy, there is a rate function or the free energy density. So we expect that there's a scaling with the number of degrees of freedom. And something similar has been found for dynamical quantum phase transitions. So we expect that there's some collapse as a function of the subsystem size. Yeah. Yes, I will show you in a second. So there's a scaling that we expect that goes like e to the n, the number of degrees of freedom. So we can try to collapse all these curves, which will then reveal exactly that. Okay, so we get to this DQPT at around 1 tunneling time. So it's a really short time effect, right? Not much redistribution has happened yet. So we can look at this collapse exactly. So here there are just a few different curves, exemplary. So there's n equal 1. So there's still something happening. If you go to larger subsystem sizes, then there's 5 and 6. And you see that mostly these curves like very nicely collapse. And you really have to zoom in into the details in order to see the sharpening emerge. And so we've actually tried to, for a very long time, to try and extract something from these DQPTs for our particular system, because there's nothing like really generic that we could learn from it. So we started digging into the details and trying to understand what gives rise to this sharpening for our DQPT. And so what we also see is that n needs to be sufficiently large for this rate function to become constant. So there is like a change if you go from very small numbers like 1 to larger, but then at some point it becomes constant, and n is still small compared to the length of the system, which is 40. And so here's just a way to extract the sharpening of the kink, just to make sure quantitatively that this is really happening. So we fit some empirical function in order to extract the curvature at the kink. And then we expand the subsystem Low-Schmidt-Echo in terms of connected correlation functions. So the idea was we wanted to understand if we look at this quantity, like how much is generally due to higher order correlations in the system, or is it really just some trivial single particle phenomenon that we see here that gives rise to this, or maybe just two particle phenomenon. And so here's an example for the 2-point correlation function. And then, the others are defined in an equivalent way. And Ni would be the expectation value of Ni on each side. That would be the trivial contribution to this quantity. Well, so let me show you, and then we can discuss. So just to highlight as a simple example what we do. So this would be subsystem 1. So this just depends on mean quantities. Subsystem 2, mean quantities, but then there's also a contribution from 2-point correlations. And we can plot all of these. So this is just from our experimental data. And these are connected correlators. So this is distance 2, this is 2 particles at different distances, 3 particles, different distances between the combinations, and 4-point correlators. Yes, yes, exactly. So it's like decomposing this subsystem observable into these different contributions. And I should also highlight that, what we see is that all of these do play a role in the sharpening, like to really understand why this sharpening of the kink occurs. We have to take all of them into account. But again, we should also see that all these are tiny, tiny effects. It's because we are at the kink. So of course, it's also highly sensitive to all of these different contributions that show up. One, two, three, and 2, 3, 4. Okay. So I don't, I don't remember from the top of my head how we defined these distances, but they are, you're looking at this one and this one, which I think just changed a minus sign. Yeah. Okay, so we see that at this kink point, like all of these contributions really matter. And now you can find this interesting or not. We did find it interesting because it sort of shows you that these higher order correlations really play a role for this sharpening of the kink. Like if we go to n equal to 6 and not 4, some of these contributions even become negative, and we need positive contributions in order to really get the kink behavior back. So in this case, at least, all of these contributions play a role if you want to understand the origin of the DQPT. Mm-hmm. Yes. So we could do the same experiment, you mean, and just make a box of 50, let's say, and look at these quantities. This is not something that we have done. I think from all the numerics and analysis we looked into and that we have done is, I think scaling L does only start to matter once the subsystem size approaches like L half, like half of your system size. If your subsystem is like very small compared to L, it doesn't really matter if you change the length of your system. Right. Well, as I said, I think because the effect of the finite size system on these small subsystems is so tiny, I don't think you would really see much change at all. Okay, and so yeah. Yeah. Right. Yeah, so this is also something we discussed for a while. So because all of these sort of would violate Lieb-Robinson bounds, like it wouldn't make any sense. So everything I told you, you could just say, well, okay, it's outside your light cone. What are you talking about? And the reason why we see any of this is really that if you look at the light cone, I mean, it's not strictly 0 outside. So there are small, tiny contributions outside. They are exponentially suppressed, but we are also exponentially sensitive to all of these effects. So it's completely fine with Lieb-Robinson bounds. It's just that we are really looking at these very, very small signals.
Higher order.
Right.
I mean, is there analytics for this? I mean, these are short time phenomena, and it doesn't sound unreasonable to simulate or even actual numerics up to time 1.
We started, so in principle you can, like all of these is also free fermion dynamics. It becomes a bit annoying to write down at some point.
No, but I mean, you've got order 1 particles and order 1 time and so on, so there doesn't seem to be any fundamental obstacle to...
I think there's no fundamental obstacle. If one would want to sit down and do it, I think it should be possible. Okay, so now we switch gears and we go from short-time dynamics to long-time dynamics and trying to understand something about the thermalization of our system. And so Hilbert space fragmentation is something that we have already looked into in the past. And I don't know if I need to motivate that here, but just to put it into context, what we do is, again, quench dynamics. But in this case, we prepare some initial state, we let the time evolve, and then we look at the steady state. So at a point where actually no dynamics is obviously happening anymore in the system. And there are 2 extreme regimes. The regime of ergodic systems, which generically happens that systems just thermalize, and many-body localized systems in the presence of disorder, where we have an emergent number of extensive conserved quantities that then lead to failure of thermalization in these systems. And now in between, especially in these constrained models, there can be different phenomena. There can also be other systems with quantum many-body scars. Here we look at systems that in the tilted lattice model, for instance, would have dipole conservation. And if you now label your symmetry sectors in your Hilbert space according to your conserved global conserved quantities like dipole conservation, it shatters into these different blocks. So you could label them according to their eigen value, according to the dipole quantum number. But then you see that if you zoom into one of these blocks, it fragments even further. So this is a phenomenon that can prevent the conventional notion of thermalization now in the presence of constraints. And so these disconnected subsectors are Krylov subsectors. And one very easy realization are tilted lattice models. So here you have dipole moment conservation, and you isolate like correlated hopping processes in the system. So I think I've drawn them here. So you can isolate processes such that single particle hopping is essentially blocked. And if you tune these on-site potentials between neighboring sites into different regimes, you can get effective Hamiltonians in second-order perturbation theory that consist of correlated hoppings. And then in the limit of sending this tilt to infinity, this ratio over the tunnel coupling, then you can show that the system fragments into many into exponentially many disconnected subsectors. And what all of these experiments, so there's also one that has been done in 2D in Immanuel's group in Garching, what all of these experiments have been doing is to prepare different initial states psi 0 and just look at different thermalization behavior. Because if you look on the previous slide, depending on the initial state, like even if your state has the same dipole moment, like both initial states have the same dipole moment, depending on the overlap with these different sectors, they can show very different thermalization behavior. And so the easiest to do in our type of experiments is to pattern different charge distributions in the initial state and then measure, look at the memory of this initial state. So the residual amplitude of that as a function of time. So in these 1D experiments, often what has been done is the amplitude of a charge density wave, you watch it decay as a function of time. And if it's non-zero in the steady state, then the system indicates that there's some non-thermalizing effect because you would expect it to wash out fully in the t equal infinity limit. So this is sort of okay, but also not quite satisfactory because you would like to know, well, how large is the dimension of your fragment? You would like to have a more direct signature of fragmentation or the number of states that are accessible to your initial state. And we have been using the subsystem Low-Schmidt echo for that. And the intuitive argument is very simple. So the idea is that, again, we have this long chain of like 40 or 50 sites. And then we look at a subsystem. And if your initial state has a high temperature or high energy density and it thermalizes, you would expect it to eventually occupy all your microstates that are available to this initial state with equal probability. So the bit string probability, which is actually what we extract, so we look at these overlaps with the initial state, should scale as 1 over the dimension of the effective Hilbert space that is accessible to the system. And indeed, like doing a little bit of math, if one describes this in a grand canonical ensemble, really having this picture that the subsystem is embedded in a larger system, one can derive a connection between this time-averaged subsystem Low-Schmidt-Echo and the thermodynamic entropy, Sn. And there are actually corrections as a function of beta, which scale as beta square, and in the limit of t infinity, essentially disappear. So this is an upper bound, but if if the temperature is very high, then this is a very good approximation. We can use the bit string probability that we extract in order to learn something about the entropy of the system, which is connected to the dimension of the Hilbert space. So by looking at the scaling of this thermodynamic entropy with n and extracting the slope, we can learn something about the local Hilbert space. So this is essentially what we do. We measure our subsystem Low-Schmidt-Echo. We look at its scaling with n, and then we extract the dimension of the Hilbert space. Here, L is the total length of the system. So if you have like a local Hilbert space dimension of 2, it would scale as 2 to the power of L. And from the scaling, we would then extract a slope of 2 if everything works properly. And now this is based on the assumption that the thermodynamic entropy is extensive in n. So essentially what we say is that if the subsystem is larger than the correlation length in your system, and it scales extensively with n, then from the slope you should be able to extract the dimension of the Hilbert space. And in order to realize fragmentation in our system, we replace this linear tilt with a staggered one. So we apply delta, an on-site potential on every other side, and we tune it into resonance. So the Hubbard on-site interaction energy is resonant with this on-site potential delta. And then we take the limit delta over j to infinity in order to derive an effective Hamiltonian. And you can already see it in the schematic here. There are then resonant correlated processes. So eventually the one that remains is connecting two particles on neighboring sites to a doublon on one side because they can resonantly hop on top of each other, making use of the tilt energy. In the limit of large tilts, this is the effective Hamiltonian that one gets. And this is fragmented. And then we can prepare different initial states. Now, in this case, we prepared two relatively simple ones, a charge density wave initial state and a domain wall initial state. And if we look at the different Krylov subspaces in the system, the domain wall state has a large overlap with the second largest fragment in the system. And the charge density wave is essentially frozen, because if you look at this effective Hamiltonian, it's not connected to any other state. So it's expected to just sit there. Okay, so we do these experiments at roughly 300 tunneling times. And then we look at the steady state of our system and analyze it as a function of the subsystem size. If we are in the fragmented regime, so here you see the two different initial states, the domain wall and the charge density wave, you see that the slope obviously is extremely different. While if we prepare these two initial states and we go into the ergodic regime, where we don't make use of this tilt resonance that gives us fragmentation, so we tune the tilt to very low values. Tilt is equal to u, so we just go to very low values in this case, and the system becomes ergodic. There's no initial state dependence left in that specific example. And this line in between is this example of a slope of 2, where your local Hilbert space would have a dimension of 2. So now this is like a bar plot of the values that we extract. So you can see that in the ergodic regime, we are a bit above. And you can now do simple combinatorics in order to understand what the local dimension of the Hilbert space is. In the case of the ergodic system, it's very simple because it just depends on the occupation you can find on each site. Ideally, if you also have doublons that do not cost any energy, I think you end up at something like 2.6 if you restrict it with our U. So it's a little bit blocked in energy. And here we measure something like 2.4. So it's very close to just saying that doublons are energetically a little bit suppressed, which reduces your local Hilbert space. And in the case of the charge density wave initial state, it's just 1, so it wouldn't actually increase much. And in the case of the domain wall, there's a combinatorics formula that you can derive, which is actually square root of 2 to the power of L. And so we are very close with our experimental results to the numerical and also analytical expectations. The charge density wave does not work as well because it's very sensitive to defects in the initial state. So we measure these return probabilities, but we assume a perfect initial state because we cannot take a picture of our state, evolve it, and know exactly what the initial state distribution was. If there are defects, then they are just statistically distributed in the initial state. So this will give us entropy in the system that we see, or that shows up in the slope of this measurement. Yeah, so this is actually something that, in principle, in a model agnostic way, your data can tell you. If there's a finite correlation length of, let's say, 2 or 3, you would expect deviations from this linear scaling. So the fact that this is very nicely linear tells you that the correlations in your system don't really play any role. Like you can like on a very small system of 1 or 2, this is already enough to understand the thermodynamics. Well, I think in this particular case, you don't need the rest of your system, so you could do that. I think what I like so much about this particular measurement is that you have like a model agnostic quantity almost, like you have this T infinity criterion that tells you something about the thermodynamic properties of your system. Like I could just do this scaling. It doesn't even cost me anything experimentally to look at this scaling because I have my snapshots. It's a chain of 50 sites, and this is just pure analysis. And I can just ask my wave function, well, are there any non-trivial correlations that I would need to worry about or not? So I think that's what I like so much about it, especially because working in these tilted lattices where we looked at fragmentation earlier, deriving these perturbative Hamiltonians, yes, you can do, and you can analyze them. But then there are also always higher order contributions, and it was sort of not so easy to actually understand everything that is going on in the system. And here you can just ask, you run the experiment and you extract the quantity. And then, of course, there's a question, well, can you use it for something that is a bit more non-trivial? Like if you have finite correlation lengths in your system, I mean, we don't have to stop here. But in this particular case, you're absolutely right. And this is just a schematic showing that the domain wall lives in this large fragment and the charge density wave is essentially a frozen state. And here, this is exactly what I wanted to highlight. We tune here the staggered potential, so it's the same fragmented Hamiltonian, but addressing the question, how large does this parameter have to be in order to enter this fragmented regime? And so I think there are a couple of interesting points to mention. So first of all, this is a finite time window around 300 tunneling times. And this curve will look different depending on which time window you pick, because these constraints, so it's a perturbative Hamiltonian, this shape will change. So these higher order contributions, when they start to matter or kick in, this depends on the time window that you look at. And here, for this particular 300 tunneling time case, you see that we seem to enter like this fragmented regime at around ratio of 10. But this diagnostic also allows you to take these curves as a function of time. So you could also now run this experiment at 1,000 tunneling times, look at how the curves behave. And eventually, because all of this is a perturbative calculation to get the effective Hamiltonian, eventually it also needs to explore the full Hilbert space again. So eventually you would expect it to be ergodic if you just wait long enough. And so I think it's just really nice because as you saw on these slides, essentially all of this was pure data. Like there are no theory curves in these plots. It's a quantity that you can just analyze from snapshots, and it already tells you a lot, gives you a lot of information about your system. I think that's why it's a quite powerful technique. Okay, and with this, I'm at the end. So just a brief summary of the different projects that we have worked on recently. And I would like to thank the team. And I want to specifically highlight Simon, who is the PhD student on the experiment, who has led the Low-Schmidt Echo project, who did really an excellent job on all of this, both experimentally and also in theory. We have 3 additional members, Irene, Alex, who worked on the rotations and the flux ladder systems, and our postdoc Zhongjong. And actually, Wolfgang spent half a year in Munich, so he collaborated with us on the cesium experiment and the teams of Anatoly and on Marcus. So thank you very much.